Good afternoon, everyone. I hope that you're still doing good. What we're looking at here is the final lesson dealing with integrating rational expressions. And this lesson can be found on page 29 of the handout. What we're dealing with today here are rational expressions as integrands that do not fall into the categories that we've covered so far. And basically what we've looked at so far is how to handle a rational expression as an integrand if the degree in the numerator is smaller than the degree in the denominator. And in example 5, the degree in the numerator is equal to the degree in the denominator. And when we get to example 6, the degree in the numerator is greater than the degree in the denominator. And essentially the general starting point for these types of rational expressions is to rewrite them using long division. Now, when we studied division of polynomials in Math 30-1, we were always dividing polynomials by binomials of a particular form. And in that class, I taught everybody how to do long division of polynomials by that binomial, and I also taught you how to do synthetic division of those polynomials by that binomial. And what I would have told my class at the time is that even though I'm teaching you long division, you don't have to use long division in 30-1. But I also would have told my class that the reason I'm teaching long division in 30-1 is that you need to know how to do long division for Math 31. And this is exactly the location of the course where that's required. So we're going to go through long division here. I'm going to use this very simple example to remind you of how long division works. You want to set things up by drawing your division symbol. It looks a little bit like a square root sign, but it's not. And the thing that you put underneath the division symbol is the numerator of your rational expression, and the thing that you put outside is the denominator. Now these things have particular names. X plus 4 is called the dividend, and x minus 2 is called the divisor. And a little bit later I'll write those words down so we can take a look at them. When you do long division, what you are always going to be doing is a series of stages. And sometimes long division will require you to do one full stage, sometimes 2 full stages, sometimes 3 full stages, sometimes 4 full stages. But each time you go through the process or stage, there are 3 steps. And the steps involve dividing, then multiplying, and then subtracting. Now, when you perform your first step in long division, which is to divide, it's important to note that you only look at the highest degree term in your dividend and the highest degree term in your divisor. And what you're going to be doing is thinking to yourself, what is it that I get when I take the highest degree term in the dividend and divide by the highest degree term in the divisor? Now I've color coded these because they're both x, so I don't want you to be confused as to which x goes where. You are always dividing the dividend by the divisor, or you're dividing the divisor into the dividend. So you're asking yourself what this is equal to, and this is equal to 1. You always take the result of the division and you write it above the division symbol. And you always write the result of the division, and in fact you write everything throughout this whole process in the column of the same degree. So the result of the division was 1. And if you want to include an x with the 1, you would write 1x to the 0, which means that the result of the division, 1, has a degree of 0. So 4 is a degree 0, so is 1. Now what you're going to do is the second step of this first stage, which means you're going to multiply the result from the first step by the divisor. But when you do the multiplication, you multiply the whole thing. So we have to take 1 multiplied by x minus 2. 1 multiplied by x is x. 1 multiplied by negative 2 is negative 2, and we keep things nice and neatly aligned. That's the second step. The third step is to subtract, and when you subtract the result of the second step, it's very important for you to remember that you subtract the entire result. We're going to have to take x plus 4 and subtract from it x minus 2. X minus x is nothing. I'm not going to write that down. And then we have 4 minus negative 2, which is 6. And this is a very basic example of long division because there's only one stage. Remember, each stage has 3 steps, but there's only one stage. And the reason why we're done is at this point in time, what you would be looking at is what you get when you divide the highest degree term that still remains underneath the division sign by the highest degree term in your divisor. And we can certainly divide 6 by x, but because we end up getting a negative exponent, we basically say to ourselves that we are done. We don't want negative exponents here. So you can't do anything with 6 over x, and we're done. And that's why I say this example is fairly basic. There's only one stage. Again, each stage has 3 steps, but once we got to the end of our division, multiplication, subtraction, we're done. Now I'm going to label all of these items. 1 is the result of the division. It's called the quotient. 6 is what we have left over, and it's referred to as the remainder. X minus 2 is what we were dividing by. That's referred to as the divisor. And x plus 4 is what we were dividing into. This is called the dividend. And what we are going to do now is rewrite x plus 4 over x minus 2 using what's called the division algorithm or the division rule that you learn about in Math 30-1. The rule is that when you take your dividend and divide it by the divisor, that original expression, in this case, x plus 4 over x minus 2, will always be equal to the quotient plus the remainder over the divisor. So in our example, the dividend was x plus 4. The divisor was x minus 2. For the quotient, we got 1. And for the remainder, we got 6. Now, how does this help us out? Well, it helps us out because the original question was, what is the integral of x plus 4 over x minus 2? But since x plus 4 over x minus 2 is 1 plus 6 over x minus 2, we can change the question to what is the integral of 1 plus 6 over x minus 2. So again, I think this is fairly basic, the idea of what we're talking about here, but I want to make sure that it really sinks in for everyone. X plus 4 over x minus 2 is exactly the same as 1 plus 6 over x minus 2. If you wanted to, you could take 1 plus 6 over x minus 2, find a common denominator to add those two together, and what you would discover that you end up getting is x plus 4 over x minus 2. And when we take a look at this integral, I'm going to write it as the integral of 1 dx plus the integral of 6 over x minus 2 dx so that I can make a point in the next example. So the integral of x plus 4 over x minus 2 dx is equal to the integral of 1 dx plus 6 over x minus 2 dx, Well, the integral of 1 dx is x. The integral of 6 over x minus 2 dx is 6 multiplied by the natural logarithm of x minus 2, and then you add your arbitrary constant. And we're done. This is the integral of x plus 4 over x minus 2 dx. Okay, let's take a look at the next example. We have to start off with long division because the degree in the numerator is not smaller than the degree in the denominator. Whenever the degree in the numerator is the same or bigger, you have to do long division. Okay, well, our dividend is 2x cubed minus x squared minus 3x plus 2. And our divisor is x squared minus 4. Remember that you are always dividing the highest degree terms when you do the first step of a stage of the long division. So the first step of stage 1 is for us to ask ourselves, what is it we get when we divide 2x cubed by x squared? Well, what you get is 2x. And I need to write that 2x in the column of similar degrees. Now I'm going to take that 2x and multiply by x squared minus 4. 2x multiplied by x squared is 2x cubed. 2x multiplied by negative 4 is negative 8x. And then I have to subtract. Don't forget you're subtracting the entire thing. So we have 2x cubed minus 2x cubed, which is nothing. We also have negative 3x minus negative 8x, which is 5x. But you can't forget about this negative x squared here. That's part of the subtraction as well. We have to take negative x squared and subtract 0x squared because the result of the multiplication didn't give us x squared. So we could write 0x squared, which means negative x squared minus 0x squared is negative x squared. Now we're going to repeat the process. This time, however, the highest degree term that is in the dividend has now been reduced to negative x squared. So the first step of the second stage is to take negative x squared and divide by x squared. We're always dividing by the highest degree term in the divisor, which I've highlighted in blue. And that gives us negative 1, which we write in the constants column. And now I'm going to multiply negative 1 by the x squared minus 4. Negative 1 times x squared is negative x squared. Negative 1 times 4 is positive 4. I have to write it in the constants column because 4 is a constant. And then I have to subtract. And remember, when you subtract, you're subtracting the entire result of the multiplication. And since we have to subtract the entire result of the multiplication from what's above, we have to add 0x in to make our mind a little more receptive to this idea of subtracting like terms. And we also need to do one other thing, which is to not forget that there is a 2 above that needs to be included in this whole subtraction as well. This is why you're taught when you learn about long division that you bring down the next item. You bring it down so that you don't forget it has to be part of the subtraction. All right, negative x squared minus negative x squared is nothing. 5x minus 0x is still 5x. And then we also have 2 minus 4, which is negative 2. So let me label each part of what we have going on here. This is the quotient. We have the divisor on the left. At the bottom, we have our remainder. And of course, what we started off with is the dividend. So what do we do with this now? What we do is we rewrite the integral using the division statement, or the division algorithm, or the division rule, whatever you'd like to call it. The integral was the integral of 2x cubed minus x squared minus 3x plus 2 over x squared minus 4 dx. But that's equal to the quotient plus the remainder over the divisor. So once again, this whole strategy is that you're taking a rational integrand that you look at and have no clue as to what the antiderivative is, and you change it. I didn't really say this, but again, this keeps coming up. If you were to take a look at the original integral, there's no way that anybody's going to look at that and know exactly what it is. You differentiate to get that integrand. So we've rewritten it. Now I'm going to go a little bit further and write it as three integrals: the integral of 2x dx minus the integral of 1 dx, or just minus integral dx, plus the integral of 5x minus 2 over x squared minus 4 dx. Now when we take a look at these three integrals, everybody knows the antiderivative of 2x is x squared minus, what is the antiderivative or integral of dx? X. Plus we have this last integral, and when you look at this last integral, you notice that it's a rational integrand where the degree in the numerator is 1 and the degree in the denominator is 2, and to boot, the bottom is factorable into linear factors. And that means that this last integral is going to be found using partial fractions. So we are off on another detour. We have to take the integral of 5x minus 2 over x plus 2 x minus 2 dx and break it up into the integral of a constant over x plus 2 plus a constant over x minus 2 using the technique of partial fractions. Which means we have 5 times x minus 2 over x plus 2 x minus 2. This is going to be equal to a over x plus 2 plus b over x minus 2. I've just spaced things out here because my next step would be to multiply every term by x plus 2, x minus 2. So I just wanted to leave myself a little bit of room here so that it wasn't too crowded. On the left-hand side, we've got some canceling happening. The entire denominator gets washed away. The x plus 2 over the x plus 2 cancels, and the x minus 2 over the x minus 2 cancels. And we are left with 5x minus 2 is equal to a times x minus 2 plus b times x plus 2. And we need to find a and b. In order for me to find a and b, I could take a shortcut here, which is to let x equal 2 and then solve for b, and then let x equal negative 2 and then solve for a. I'm not going to do that. I'm going to use the more analytical approach, which is to expand everything out. I will have ax minus 2a plus bx plus 2b, and then I compare the linear term on the left to the linear terms on the right. And I also compare the constant term on the left to all of the constant terms on the right. I am assuming that if you're watching this video, so you followed me along this far, even though it's not part of the course officially, that you've also watched Wednesday's lesson. And this was the technique that we were forced to use Wednesday. To be perfectly honest, I have taken a calculus course in post-secondary. Now, this was a long time ago, but at that time, the shortcut was frowned upon. The proper way, I was told, is to use a system of equations. And I will give you the reason why you're not technically allowed to use the shortcut. When you use x equals 2 to eliminate your a's, what you are doing is using a non-permissible value, because in the original expression, x minus 2 was in the denominator. So you're not allowed to use x equals 2. This was the reason anyway that was given to me as to why that shortcut, although it works, shouldn't be used. Anyway, what we end up with here is a system of two equations. One of the equations says that 5, the coefficient of x, has to be equal to a plus b, which is the sum of the coefficients of the x terms on the other side. The other equation is negative 2 has to equal negative 2a plus 2b. There are a number of ways for you to proceed from here. I'm not really a fan of solving by substitution. You could rearrange the first equation for a and substitute the result into the second equation. My favorite technique of solving systems of equations is to use elimination. I suppose what I could do is I could divide the bottom equation by 2 and add the two equations. I'm going to go ahead and do that. Negative 1 equals negative a plus b. On the top equation, I have 5 equals a plus b. My thinking here was that by dividing the bottom equation by 2, I would have negative a in it, which if I added to the positive a in the top equation would eliminate the a's. So when I add these two equations, I get 5 plus negative 1, which is 4, equals 2b. And that tells me that b is equal to 4 divided by 2, which is 2. If I want to find a, then I can use the fact that 5 equals a plus b. And b we've already established is 2. Well, that tells me now what a is equal to. A is equal to 3. That takes us to the end of our major detour. We had said, this is where we left off, that the integral of 2x cubed minus x squared minus 3x plus 2 over x squared minus 4 was equal to the integral of 2x, which is x squared, minus the integral dx, which is x, plus the integral of 5x minus 2 over x squared minus 4. But we have learned that 5x minus 2 over x squared minus 4 is a over x plus 2. We discovered that a was 3. And it was plus b over x minus 2, and b turned out to be 2. So we are almost done. What we have to do now is integrate those two terms. So we have the integral of 2x cubed minus x squared minus 3x plus 2 over x squared minus 4 dx is equal to x squared minus x plus, well, what's the antiderivative of 3 over x plus 2? It's 3 multiplied by the natural logarithm of x plus 2 plus 2 over x minus 2, anti-differentiated gives 2 times the natural logarithm of x minus 2 plus your constant. So the original question, this was the question, has an answer of x squared minus x plus 3 ln x plus 2 ln x minus 2. Once again, this integral is something that we got the answer to in a very indirect way. We had to use long division first to break it into these three integrals. Once we had those three integrals, two of them were things that we could handle just in our minds. Antiderivative of 2x is x squared, antiderivative of 1 is x. But the third integral is something that we had to take a detour to evaluate. And the detour was to break it into partial fractions by letting 5x minus 2 over x plus 2x minus 2 equal a over x plus 2 plus b over x minus 2. Once we did that, then we could finally come up with the answer. So we get to the answer here in a very roundabout way. We don't go directly from the integral to the answer. That's an impossible task. And that takes us to the end of rational expressions and integrating rational expressions in terms of what I would teach in the regular Math 31 class in high school. There are going to be rational expressions that you cannot integrate using any of these techniques. You're going to discover that that happens when you have a quadratic unfactorable denominator. Now, we did have an example on Wednesday where we had a quadratic that was unfactorable, but we were lucky enough that the method of substitution worked. Substitution will not always work. And in those cases, you would have to do something that we have not learned about. You would either have to use trigonometric substitution, which seems really weird that you would use trigonometry with a non-trigonometric integrand, but you would, or you would use inverse trigonometric functions. Anyway, that's it for all of the integration that I would teach you in high school. We're not together, and again, I've expressed my regret over that. I really wish that we had been together over the past few months. Math 31 is one of my favorite courses to teach in high school because of the interactions that I have with students on a really, really high level in terms of math. And we just didn't get to have those one-on-one interactions. If we were in class, I'd be telling you all about the final exam. And then when you leave the final exam, normally I shake everybody's hands and I wish them well and I talk to them for a few minutes. I don't get a chance to do that this year. So the best I can say to you is that I sincerely wish you the best of everything in the future. Work hard, have fun, and you'll do very well in whatever you decide to pursue in your life. I hope that you find something as a career that you enjoy doing every day, that you look forward to doing every day. That's how I feel about teaching, and I hope that you can find something like that in your life for a job. Anyway, good luck next year. Take care. And if you're ever in the neighborhood and you decide that you have a few minutes to stop by and chat, I would love to see you and talk to you. So that's it. That's all. Take care of yourselves, okay?